Hi, everyone. My name is Max Fine. My project is on using the 25-meter radio telescope outside to look for FRBs. My supervisors were Dr. Tamo Jan Dijkma and Professor Jason Hessels. This is a photo of me working in the DRT. Fast radio bursts are very bright radio transients from other galaxies, and 2%-ish are known to repeat. No one knows what causes them, but the more accepted theories are neutron stars or magnetars. And they're very bright. Their isotopic energy is 10 to the 36 to 10 to 41 ergs, about the equivalent energy output of the sun in 10 days. And one of their defining characteristics is dispersion, which is a frequency-dependent arrival time delay. So this is the first FRB detected, and this is the dynamic spectrum. So it's frequency on the y-axis and time on the x-axis. And you can see the arrival time delay. That's it, right? So more on dispersion. It's caused by free electrons in space that cause the arrival time delay, and it has units of parsecs per cubic centimeter. So it is a column density. And so people use this as a probe of free electron density between us and whatever we're looking at. And then here's the full equation for the arrival time delay too. So quiz question for the audience. The Crab pulsar is located at 1800 parsecs away, and it has a DM of 60 parsecs per cubic centimeters. What is the average electron density between us and the Crab pulsar? And then if you're interested in the first right answer gets a box of mac and cheese.
Second person gets 3.
Stay on this now.
Inverse cubic centimeters.
Oh, 0.0333.
Yeah. 1/30.
Nice job, Joe.
Okay, so the project's motivation, there was a recent, as of January 2024, Nature paper, which used small 25 and 32-meter radio telescopes to look at FRBs. The highlighted names are people associated with Astron. The highlight might not be the most accurate highlighting I've done. And that's really cool. So they looked at 2,000 hours and they made many detections. But there's a limited number of radio telescopes in the world, and they have a limited number of observation time. But we have a 25-meter radio telescope like outside, and it doesn't get used that much. So why don't we use the DRT? And then more about the Nature paper's results. They used a Westerbrook 25-meter dish. And they observed at 500 hours in P band and 500 hours in L band. They made 24 detections, and then one of their key results was this power law plot of the hyperactive FRB burst rate versus energy. And they found that it was a broken power law distribution, indicating that maybe non-repeating FRBs are just really bright bursts from repeating FRBs, and they're more rare, which is interesting because other studies have shown that repeating and non-repeating FRBs have different burst characteristics. And then this is the DRT telescope. So this is me with the DRT, and it's run by volunteers at Chemros. And it recently has a hydrogen maser clock. It's actually this Westerbrook's clock. Paul set up a big cable. Thanks, Paul. So it can be used for VLPI if you want. And it observes simultaneously in L and P band. But Westerbrook only observes in either P or L band. And we record data at about 1 gigabyte per second in baseband, or about 1 gigabyte per minute for filterband data. And the sensitivity is comparable to a single Westerbrook dish. We're about 80% as sensitive at P band, about 20% as sensitive at L band. Cool. And you have to be physically inside of the little telescope cabin to record data. So the project goals are to have fun, but the main technical project goal is to build a real-time FRB detection pipeline for the DRT. If I'm very lucky, maybe detect an FRB and also do analysis on the Crab pulsar. So having fun was very easy. I had a great time at Astron. Thank you so much for having me. I made a bunch of friends. But back to the real goals. So building a real-time FRB detection pipeline. Here's some of our search characteristics. Because we don't know the DM very well, because they just come to us from A telegrams, we're using a plus or minus 10% for the DMs. And then we have a boxcar search between 1 and 30 bins and a 30-second integration for RFI. And we take data in chunks of about 10 minutes before we process it. So we have the antenna, which goes into a software-defined radio, and then that goes to our computer, where we record baseband data through a RAM. We don't have a circular buffer, so we just record it to our RAM. And then we also record filter bank data. And then about every 10 minutes, we run a bunch of Presto commands, which does RFI, single pulse search. And then we cluster, and then we run another machine learning program, fetch. And then if fetch finds something good, we slice out and save baseband data, so we make a diagnostic plot. So this is an example of one of the diagnostic plots that we make. This is for one of my observations of the crowd pulsar with a FSNR of more than 200. And most of the pipeline is again on Presto, which is a CPU-based single pulse search method. So Presto, we use RFI find to cut out as much RFI as we can. DD plan comes up with the method for dedispersing the data. And then prep subband actually does the dispersion. And then single pulse searches for single pulses using boxcar search convolution at different DM trials outlined by DD plan. And then finally, we make candidates. And then the candidate file basically is an H5 file. That's the contents of this. But after we do that, most of our candidates are still RFIs or doubles because we have multiple DM trials that we see it at. So we employ 2 machine learning techniques to help us with this. The first is DB scan. This is a clustering algorithm. So if we have pulses that are seen at multiple DM trials, this tells it, actually, that's this one pulse. And it's also helpful for cutting out a couple more RFI points. And then after that, we run fetch, which is the convolutional neural network. It basically looks at the H5 files, the dynamic spectrum, and the DM versus time plot. It looks like a bow tie in a straight line. It's like good or bad. And that saves us from having to look at the files by hand. And then when fetch makes a good detection, we save baseband data, which is really useful because the baseband data is at a much higher time resolution than the filter bank data. And it has the hydrogen maser timestamps that we use for DLBI to localize FRBs, for instance. This is on DB scan clustering. So times on the y-axis and DMs on the x-axis. Colors indicate clusters, and then the size of the circle is how bright the pulse was. So before clustering, we had about 1,600 sources, and then after clustering, we go to 150, which is pretty good for limiting how many sources we see. And the right-hand plot is a zoom in of the same one on the left, so we can distinguish between the yellow and the blue dots as 2 different clusters, between like the gray and the kind of brownish orange as well. But the colors do repeat, so the same yellow, it's not the same yellow clusters. And then a measurement for how good clustering works is called a silhouette score. If it's above 0.7, that's good, goes up to 1. And this had a score of 0.88, so I'm pretty happy about that. And then after clustering, if we still have more than 800 candidates in the filter bank file, we skip processing the rest because that's just RFI. So now we're on the FRB detections, which would be here if I had any. Thanks. So I was unlucky this summer. There were no super bright hyperactive FRBs. I did put in many hours looking at FRBs, but I was unlucky. But even no detections is important science because Westbrook managed to make several detections of an FRB. So 1 month ago today, the 21st of July, Westbrook detected a 300 SNR source, which we would have been able to detect the DRT if I was observing at 2 a.m. our time. Unfortunately, I was not. And then last Thursday, Westbrook also made a detection at 11 p.m. our time when I was in the telescope, but unfortunately that data had a bunch of RFI in it, so the pipeline didn't finish running. And I looked at the filter bank file by hand, but I couldn't find it with all the RFI. That's okay, because we still contributed to the pulse rate of the FRB. And then this is my analysis on the crab. So I observed the crab for about 30 hours, and I fitted a power law index using the method of maximum likelihood as outlined by, I don't know the paper, James et al. From 2018. And I'm only doing the fitting from the data to the right of the red dotted line. And the power law results are almost consistent with Barrett et al. From 2019. And this is a similar analysis to what the Nature paper did, but on a crab on the crowd pulsar instead of a hyperactive FRB. So in summary, the DRT now has a real-time FRB detection pipeline that's capable of joining these high cadence FRB observations. It's a question of when, not if, that the DRT will make a super bright FRB detection. And when it does, it will have baseband data that can be used with VLBI and other science. The pipeline is open source. The next step for the telescope is to make a nice directions document and to train the volunteers to be able to use the telescope for observing FRBs. And I hear a bunch of the PhD students want their own office, and you know, the DRT has windows outside you could use as an office, as long as you take observations. And then I think the DRT itself is getting some upgrades in terms of bandwidth and sensitivity. And Cameras also has a Mastodon bot, so we could post the good candidates to Mastodon. Thank you.
Thank you for the lovely talk. Have we got any questions for Max? Sana?
Yeah, so you currently have the pipeline that will register just like a bright event happening, right? And it will look for a dispersion as well, I assume, to filter out RFI as well.
Yes.
So I am very interested in very transient sources, but they tend to last a bit longer than FRBs. So what would you say would be the longest event you could record and respond, like recognize?
I think that's limited by the longest boxcar that we're using in the boxcar convolution, which is 30 bins. So I think we're only sensitive to the millisecond long transients.
It's a bit short for me, but we were
What size transients do you look for?
seconds enough.
Ah, okay.
Andre?
The RFI seems to be a bit of an issue if I understand you. I don't know how your RFI detector works, but would it help to have a better detector, or is that just not enough good data level?
A better RFI detector always is good. We're mostly using RFI fine from Presto. And then we just ignore data files that have too much clusters in the map that we do clustering too.
Okay.
May I note that your detector here will flag and burst as well?
Okay, we can talk.
So in terms of the RFI environment difference between Westerbork and Dwingeloo, do you, how much worse is Dwingeloo relative to Westerbork?
Well, I don't look at that much Westerbrook data, so I can't say for sure, but I don't think they have as many tourists with cell phones taking photos next to the telescope. I think we're a bit worse.
Yeah. Do mobile phones broadcast an L-band? Yeah.
But the Dwingeloo feed is not cool with the rest of the
I understand the sensitivity difference, but if I just didn't know how much of the RFI environment's recognized.
There's also like a building with 200 people.
We have very bad.
I thought we used Faraday cages, don't we? Finally teensy.
Very bad situation with LTE towers. One of the LTE bands is protected and a circle of 60 kilometers around Westerbork.
Yeah.
They don't use that LTE band.
Yes.
And that circle ends in a Ruinen.
Yeah.
From the east. So if we're looking in the south, we're looking at an LTE tower.
Oh,
So that's quite bad as well.
frustrating. Case, and then Ilse.
For the crowd pulsar, how many folks did you end up protecting?
Oh, go back to it. So this is after, the N here is after, the N is how many pulses, right, the red line, so about 1,500. And that's a couple thousand, tens of thousands, all seven.
Ilse, do you have a question?
Yeah, no, I was wondering about we can potentially automate this process if the telescope just have it running. The telescope always have something.
I think you can automate it. The reason they have someone there is more for safety. You have to turn on an engine for the telescope to move. So like the pipeline will run automatically, but you still have to be in the cabin.
Yeah, this is basically first half because it's a historical instrument and it has its manual how to use it safely. But secondly, tourists are very good at ignoring no access signs, and we regularly have to send them away.
You can
House right there. as well, right?
Yeah, dog or a wolf, wonder. Anyway, any last thoughts or questions for Max before we finish up? No, if not, let's thank Max one more time. Thank you, Max and Laurel, and so next week we'll have the last summer student talk as well, yeah, enjoy your week, guys, and I'll see you next week. Thanks for joining people online, if they have not.
Hi.
Hi, guys.
Thanks for making,
That's right.
yeah. I thought it was- The beams,